Okay, welcome. Today we are going to be talking a little bit about equilibrium and what exactly it is. So, I want to start off talking to you about this bungee jumper. Suppose a guy jumps off a bungee. He's going to be jumping around, swinging back and forth, going up and down crazily for a while, but if you let it run long enough, eventually he's going to reach this point where the elastic tension in the bungee is equal to the force due to gravity that's pulling down on our bungee jumper. So it will take a little time, but eventually those two opposing forces are going to come into equilibrium, and the bungee jumper will stay relatively still. And he'll stay that way essentially forever, as long as people are willing to let him hang there and as long as he can stand it. So that's one type of equilibrium. Let's talk about another type of equilibrium. Let's say that we have a brand new high school and no one knows each other. So it's a brand new high school, no one's ever seen each other before, no one's ever gone to high school or other middle school together before. So there's 300 girls and 300 boys. Now, if we are real clever here, guys, we can actually figure out the total number of students, 300 plus 300. Say it with me now, it is 600 students total. Kind of important thing to keep in mind as we go through. Now, as you guys know, what tends to happen in a high school is we might form some romances here. This nice young lady here sees a young fella that she likes, and they form a happy little couple. Now, sometimes true love doesn't last in high school, unfortunately, and these couples that we have here, after a week or two of holding hands and going to the movies and doing all sorts of wholesome activities, they might eventually break up, decide they're better off single. That tends to happen sometimes. So here's what I think would happen. Eventually we'd reach some point, let's say at about the middle of the school year. It would take some time. Remember, there's no couples at all initially. It would take some time, but eventually the number of single girls, single boys, and couples would remain constant. Now, what's important to recognize here is I'm not saying it's the same single girls, single boys, and couples, but rather just about the time that one new couple forms, another couple breaks up again. So we kind of get this balance, we kind of get this equilibrium. So we would say that equilibrium had been reached when there was no net change in the number of single boys, single girls, and couples. Now, remember before, when we figured out how many total people were in this high school? Do you remember? Say it with me now, kids. There was 600. Is there still 600 people in this high school? Well, of course there is, because 100 couples represents 200 people, so 200 plus 200 is 600. So the number of high school students has not changed. So that's what we call equilibrium, when these amounts are staying the same. At any given moment in this high school, there's 200 girls, 200 single boys, 200 couples. Not the same single girls, not the same single boys, but just about the time that we make one of these, another one of these couples breaks up again, so those amounts stay steady. Now, what that is known as is something called the dynamic equilibrium. So it's weird, it's kind of almost sounds like an oxymoron, but things are changing but they're staying the same. So there's a back and forth that's occurring, but the overall amounts actually are not changing. It does not happen instantly, it takes some time, but in many systems we're going to reach an equilibrium like this. So, as you might guess, we can relate this to chemical reactions. It turns out that there are some chemical reactions that go backwards. All of them can technically go backwards, but some of them go backwards quite a bit. For instance, in this particular reaction, like here, we see SO2 plus O2 making SO3. It turns out that just about the time you make some SO3, some of this SO3 is going to transform back into our reactants again. You may have noticed every once in a while a double arrow in some of our reactions. A double arrow is used to indicate the sort of back and forth nature of some reactions. Now, there are some reactions that go backwards to a large extent. It might be that this reaction tends to go backwards even more than it goes forwards, and we're going to talk about all this kind of stuff. Some reactions go backwards hardly at all. In other words, our reactants would just transform into product, and barely any of it would go backwards, and anywhere in between. Reactions that do not go backwards are said to go to completion. So if I had a reaction where pretty much 100% of my reactants turned to products and there was no backwards reaction, I'd say that's going to completion. Now, so far in this course, we've either looked at reactions that go to completion or we've completely ignored the backward aspect of certain reactions. If you think about it for a second, we've totally ignored the idea of going backwards. We sort of had to lie to you. I sort of had to lie to you because it gets complicated. It gets stoichiometry in particular. It gets a little complicated and the reaction goes backwards. So we had to kind of ignore that. We had to kind of sweep it under the rug until we were ready to comprehend this kind of stuff. And now, ladies and gentlemen, I think you are ready. So we're ready to talk about reactions that go backwards. One of my favorite websites that we've looked at before, FET, has a little animation, and kind of like one of those cooking shows where they start telling you how to make a dish, and then they pull it out and it's already finished, in advance. I've gotten this ready in advance, this animation. I've downloaded it, and we're not going to keep those ink annotations. So we will look at this one that I've prepared in advance, gotten ready to go. I'd advise you, if you'd like, you could try out this animation. You can follow the link that's there in the PowerPoint, available for download. We can adjust the activation energy here. Remember the activation energy? We talked about that last year. So we've got reactant A, and we've got product B. Reactant A can turn into product B. Notice there's a double arrow. This reaction can go backwards. We can adjust how many molecules we want to start off with. Let's start off with 50 molecules of A, just for kicks. We could change the temperature if we want. Let's leave it at 300. So what we're going to do is we're going to start this simulation, and at the beginning there's 100% A and no B, and whoop, lo and behold, we've formed a couple of molecules of B. But so far the reaction hasn't gone backwards, but these B molecules, as we keep an eye on them, if they can manage to jump up and overcome that activation energy, they will turn back into molecules of A again. So as the reaction is proceeding, more and more of A is turning into B. Oh, there you go. One of the B's just turned back into A again. And there we go. Now we're getting a little bit of back and forth happening. What's going to happen as this reaction proceeds is we're going to get more and more B and less A. It will take some time. In fact, I'm probably not going to let it run till it actually finishes. It might take 4 or 5 minutes or so. But eventually, as time goes on here, there will actually be more B than A in these chambers with the way that I set it up. And so at some point, we can follow up here. Right now, there's 41A and 9B. We can see up here by where my cursor is in the corner. At some point, these amounts are going to be staying steady. When those amounts are staying steady, that's when we've reached equilibrium, approximately. I mean, they're always going to be flickering back and forth a little bit, but whenever these numbers start staying approximately steady, then we know that we are at equilibrium. So, kind of an interesting little demonstration thing to play around with a little bit. I'm going to go ahead and stop this now, and we're going to go back and so that reaction that we were just looking at, and the way that we were looking at it in the previous slide, we were showing it in the typical way that you show these reversible reactions. This reaction, H2 plus I2, and we have kind of a double arrow, makes 2HI. Now when you write down a reaction like this, the one going in the normal way, left to right, that's known as the forward reaction, and the one that's going in the other direction, opposite the way we normally read, is known as the backwards reaction. So when we start off with something, the system is going to move towards this equilibrium where there's no net change in the amounts of substance. And this is something that IB loves to ask about here. What's going to be true when we get to that point is that the rate of the forward reaction is going to be equal to the rate of reverse reaction. That's something that's going to be true when we're at equilibrium, that those two rates are going to be equal. So the net change, there's no net change, and those two rates are going to be equal. So it will be turning into product at the same speed that that product is turning back into reactant again. So for instance, what we see in this graph is it's basically got my two types of reactions split into two different graphs, or kind of showing you the information in two different ways. We could call this experiment 1 here. In experiment 1, what they've done is they're just kind of, in a way, focusing in on the forward reaction. Here's concentration, here's time. We looked at some of these kind of graphs in our kinetics unit. Here we're focusing on a different thing. Kinetics is about how fast reactions take. This is more about how much stuff is going to be around when the reaction actually comes to equilibrium. So if you notice, at time 0, or when they start, they're graphing H2 and I2 on the same line. I guess they're starting with the same amount of each, so it ends up on the same line. So they're starting out with a certain amount of H2 and I2, and they're starting off with 0 HI. And as the reaction goes on, reactants are turning into products, so there's less and less H2 and I2, and there's more and more HI. Now there's kind of a back and forth happening here all along that this graph isn't going to show us, but at some point these amounts stop changing. The concentration is holding steady, and that is when we're set at equilibrium. Right at this time, whatever time that is, that's when the reaction reached equilibrium. Now our kinetics unit was about how long did this take? How many seconds was that? That's what kinetics is about. In this unit, it's more about how much do we have. So those are the differences between those two units. In this, let's call this experiment 2, what they did instead is they're focusing in on the backwards reaction. So this reaction up here at the top proceeding back in this direction. So what they did is they started with no H2 and I2, so none of our reactants in the forward reaction, and they started off with all of HI only. So what happens is the reaction starts to proceed backwards. Backwards, you know, when I say backwards, I'm talking about this top reaction that I wrote up here. The reaction starts to proceed backwards, so to speak. So HI is turning into H2 and I2, and at the same time, the H2 and I2 is turning back into HI again, so we got this dynamic equilibrium thing happening. But what's kind of interesting is it ends up in the exact same equilibrium state as it did in experiment 1. The amounts of each end up leveling off, and they end up equaling out in both experiments. So it doesn't matter whether they started with only H2 and I2 in experiment 1, or whether they started with only HI in experiment 2, the equilibrium state ends up being the same. That's what this side is talking about. It doesn't matter what you start with, H2, I2, HI only, or even some mix, eventually you're going to come to the same state at the end. The same equilibrium state. Now the temperature would affect this. And that's actually the only thing that would affect this equilibrium state that you end up reaching when it comes to the equilibrium constant, which we're going to talk about in a second. So, the equilibrium constant, really important equation in this section. Now, it looks a little more complicated than it probably really is. So here we have this generic reaction. A plus B makes C and D. And what's important is a few things. These brackets, which we looked at before, they mean concentration, so call it molarity or mole per cubic decimeter. Basically, they mean concentrations, and that's a good enough way to think about it. What's also really important is here are my products. Products go on top, and my reactants go on the bottom. And then if there's any coefficient, that becomes a power. And we get this number here, which is called the equilibrium constant. IB tends to refer to it as Kc. You will see it from time to time, probably more commonly, in my experience, referred to as Keq, or sometimes even just K. IB tends to use this, Kc, so that's the one that we're going to talk about. Now, what I don't want you to get confused on is there is a rate constant K that we looked at in the kinetics unit. That's a totally different thing. It describes something completely different. So when we're thinking about K, just make sure that you distinguish between these things. The rate constant K is for how fast reactions go. This is more about equilibrium. So we can do this quantitatively. We can get some numbers. What we have to do is we have to figure out, once a reaction gets to equilibrium, we figure out what is the concentration of everything. And then that's what we put into these boxes. And we'll see some examples of this in a second. But let's first kind of just start off generally how the equation works and how we're going to even set it up. If this is our reaction, this is the same one that we were looking at in those graphs earlier. H2 plus I2 makes HI. If I'm going to write what's called the equilibrium expression for that, it's pretty simple. I just need to remember that products go on top. Products are always on the right. Whatever way you chose to write the equation, the things on the right are the products. And the reactants are over here. Product's going to go on top. Reactant's going to go on bottom. And we're going to get something that looks like this. And again, what goes in here are concentrations at equilibrium. So once we know those concentrations, once we do an experiment and figure out how much stuff is around at equilibrium, we could put numbers in here and get an actual number for this constant. But for now, notice, again, the product's on top. The coefficient becomes a power, in this case a power of 2. There's an imaginary understood coefficient 1, which have coefficients of 1 here, but since coefficients of 1, mathematically, they don't change anything, so we don't need to have those. So if you're writing an equilibrium expression, that's what you're doing. You're taking this thing and you're turning it into something like you see at the bottom. Now, we need to talk about something very serious here. So we need a serious man, Samuel L. Jackson, to help us think about this. Think about this equation. As I'm always saying, you don't want these things just be random arbitrary symbols on a paper. You really want to think about it, think about what it means, and if we can kind of tie into some math and think about what the math means and how it all fits together, we would be so much better off. So let's think about this for a second. What this number is it's telling us how much stuff is going to be around at equilibrium. Remember, some reactions, and the reaction again is hydrogen plus iodine makes HI. And we don't know really anything about this reaction, but we do know that it goes backwards to some extent. It might almost go completely in this direction and barely backwards at all. So a bunch of this around equilibrium and very little reactant. Or it might only make a tiny bit of HI, and at equilibrium there'll still be a lot of our reactant left. We don't know. In fact, Kc can tell us about how much stuff is going to be around at equilibrium. So let's think about the situation where this reaction, when it gets to equilibrium, there's a bunch of HI and very little of H2 and I2. That's this situation right here. What that means is this top number is going to be large if there's a lot of it around at equilibrium, and these bottom numbers are going to be small. So in that case, this Kc number is going to tend to be large. If you take a big number and you divide it by small numbers, Kc ends up being a large number. On the other hand, when the reaction gets to equilibrium, if there is lots of reactant and very little product, so now we have a small number up here divided by a larger number. That's going to tend to make this number tiny. So basically, the value of Kc tells you how much product you have around at equilibrium. And the bigger Kc is, the more product there is at equilibrium. So in case it's not clear yet, on the next slide I'm trying to make it clear how important of a concept that this is. This is a slide that's about how we can interpret different values of Kc. If Kc is large, and just to pick a number, I mean there's no real dividing line here, but if that number's large, like bigger than 1,000, let's say, the backwards reaction is barely happening. In other words, like in my generic example here, pretty much all of the A and B is going to turn into C and D, and we don't have to worry too much about the reaction going backwards. If Kc is very small, and again, just to pick a number, 0.001 or 10 to the minus 3, well, then the forward reaction is barely occurring. And so when we get to equilibrium, really mostly we would have A and B, and there'd be just a tiny bit of C and D around. And if Kc was sort of medium, there's going to be measurable amounts of everything at equilibrium, so there's going to be kind of an even mix. Now, to just sort of throw a number out, or actually it's an important number, it's if Kc is larger than 1, it is said that products are favored. So when we get to the point where we're actually plugging in numbers, and we'll do some examples later, if we're getting to the point where we're actually plugging in numbers and this value, this Kc value, turns out to be larger than 1, it means that products are favored. If it's less than 1, it means reactants are favored. So if you ever asked that, if you're ever asked to calculate a value of Kc and asked if reactants or products are favored, it's really as simple as deciding if Kc is bigger or larger than 1. Now, got a little bit more to talk about here, but before we go any further, if this last part has kind of lost you, I'd maybe advise backing up or stopping and thinking about it a little bit before you go any further, because as I've said here, this is a super duper critical concept for this unit, equilibrium, and the next, acid-base. So this is really something we need to have a handle on. But just a couple more things. There's only one thing that changes a value of Kc for a particular reaction. There's only one thing that changes the value of Kc, and that's temperature. If Kc is large, yes, it means that products are favored, but it doesn't mean the reaction's fast. Remember that demonstration we were looking at a while ago with A turning into B from FET. It might take 1,000 years to get to equilibrium, a certain type of reaction. So Kc does not mean the reaction's fast. It just means that when it finally does finish, whenever that might be, if Kc is large, there's going to be a lot of product and very little reactant. Another thing that's really important is when we have a reaction where there are pure solids and pure liquids, we are not going to put them into this equilibrium expression. They're simply just not going to be there at all. Now remember, solids and pure liquids, solutions, aqueous stuff, yes. Solutions definitely go in here. But actual pure liquids, no, they do not. Nor do solids. And just kind of to touch again on something I've touched on earlier, we've basically ignored this aspect of things so far to kind of get us through. Ignored this aspect of backwards reactions. It's to make things simple when you're starting off, but now is the time, unfortunately, when we have to stop ignoring it. This is a very, very serious real-life consideration. If you think about it, if you're making a product, if you're making, let's say, ammonia, for instance, it is a very, very important industrial-produced chemical, and we're going to talk about this in some detail later, but if your job is to produce ammonia, this reaction actually does go backwards if you don't carefully modify the reaction conditions. This reaction actually does go backwards quite a bit. So if you're trying to make ammonia and you have a reaction that goes backwards, so the stuff you're trying to make and use as ammonia is turning back into reactants again, well, that's obviously frustrating and you don't want that to happen. So there's some things that chemists can do to kind of help out with that situation. So this is an important real-life situation that real chemists have to deal with. That's it for this part. And then we're going to look at some examples of how we actually put numbers into that equilibrium expression next. So I'm going to close out here, and we will stop for now. Thank you. Okay, so we are going to continue our discussion of the equilibrium constant and the equilibrium expression by getting a little more quantitative with it. So this is the page in the workbook that you want to be working with. It says the equilibrium constant up at the top. If at any time while I'm going through this, if you're a little lost, a little confused, try stopping, back up, go over it again, maybe make a little more sense the next time around. But I definitely would suggest that you go through this as I go through with it and add the stuff here into your workbook. So there's a lot of information up here. It talks us about how sometimes we call the equilibrium constant KEQ, sometimes KC, sometimes even just K. Despite what even the worksheet might say, we're going to usually use KC because that's what IB uses. We should probably make sure we understand the generic expression here and actually write in this generic equilibrium expression. So we're going to take this equation and write an equilibrium expression for it. The KC part is already written in there for you, but I'm going to write it in again so you can see it. And what's important to remember is that we put products on top. So since our products are always written on the right, whatever is on the right is always considered to be our products. Those go on top. If we've got any coefficients in front of them, those become powers. So a to the a power over b to the b power. So that's the generic form. You should probably go ahead and write that in to remind yourself of that. There's some good information here. This is all stuff that we already talked about in the PowerPoint presentation and portion of the video. So I might refer back to some of those as we go. But let's just go ahead and look down at these examples. Now I know you probably can't read this, but I think we'll manage to make it through here. We're going to do example 1 together, and it says write the equilibrium expression of this reaction. That's what we need to do in A. So we're going to go ahead and do exactly that. So the equation, this is one that we happen to have seen actually in that PowerPoint. This exact same equation came up in that PowerPoint, but we're going to take a look at it again. It's important to note these are all gases. That actually does become critical here. So when it says in A to write the equilibrium expression, you do exactly this. You say Kc equals, you need that part, or it's wrong. Products go on top, so we're going to put a bracket. Bracket stands for molar concentration. Since there's a coefficient of 2, it becomes a 2. Reactants go on bottom. There's no coefficients, or there's an understood coefficient of 1. Either way, it doesn't really matter. So that is it. A is complete. Exactly that. That's an equilibrium expression. No numbers written in, nothing generically done. The equilibrium expression for this one is exactly that, and that's exactly what we should have for A. And again, if any time you find yourself a little bit behind or you don't understand something, go ahead, pause the video, back it up a bit, go through it again, and see if it can make sense to you. But we're going to go ahead and take a look at B. It says to calculate KEQ, and KC are the same thing, and then it gives us some values. So let's just kind of like write in those values that it gives us. H2, I2, and HI. So it tells us that we have 1.56 moles of this, and it tells us both of these are 0.22, and those values are all in moles. It also tells us in this problem that this is a 1.0 liter container. Now this is actually important because these brackets mean molarity. They mean molar concentration. So before I put anything into this equilibrium expression, it has to be a molar concentration. Hopefully you remember the molarity equation. It's this. And so what we're going to do is we're going to turn all these values into moles before I put them up into this equation. Now the good news is they've made it easy for us in that it's a 1 liter container, because if I solve for molarity, let's say for HI first, I'm going to put 1.56 moles here. My volume is just 1. So for all three of these guys, I'm only going to be dividing by 1, so that makes it really easy because the number of moles and the number of and the molarity is always going to be the same, since we're going to be dividing by 1. Now if it was a different size container, like a 2-liter container that you're going to see in one of the other problems, well then I'd have a 2 down here and I would have a different answer, but they've made our life a little easier given that they've told us it's a 1-liter container. So what I'm going to do is I'm going to put all three concentrations into my equilibrium expression and simply solve it. So I've already figured out the concentration of the HI is 1.56. Don't forget to square it. And both of my concentrations here are 0.22. So I just need to solve that little mathematical expression. So I get out my handy-dandy calculator here. I don't know if you can see what's going on this calculator, but I'm going to take the 1.56, we're going to square it, and divided by, it's really important to remember to put those bottom terms in parentheses, close parentheses, and so we get 50.28. Now let's talk about a couple of things. Let's talk about significant figures. 3 significant figures, 2, 2. This answer should probably have 2 significant figures. The only way to write that really would be to go like that, 50 with a decimal. Now what I hope you're thinking is, what unit goes after that, Mr. Los? Because I know you always think about units and what unit that we should be using. We could probably come up with a unit here by canceling and all that stuff. It's possible that it would completely cancel out, but by tradition, equilibrium constants are always considered unitless. So we're actually not going to attach a unit to this number. We're just going to call it 50 with a decimal in the end, just like that. That's the way that we're going to answer this question. Again, and we're all finished. That's the answer to B. So if you didn't quite grasp that, maybe go back and take a look at example 1. But what I'd like you to do right now is I'd like you to pause the video for a second. I'd like you to take a look at example number 2. Actually, sorry, one more thing before we go on from this one. It asked us if reactants or products are favored in this reaction. This is actually a really simple question to answer, and it relates to something that we talked about. It relates to something that's written on this bullet right here. A Kc value of greater than 1 means products are favored or over reactants. A Kc of less than 1 means reactants are favored over products. So it's pretty simple. This number is bigger than 1. It means products are favored. By that we mean we should expect to see, generally speaking, we should expect to see more product than reactant around equilibrium. We've got a decent amount of all of them, but more product than reactant. In fact, I mean, even just looking at these numbers here, you can see there's more product than reactant. But what I'd like to do is go ahead and pause this video for a second, see if you could figure out example number 2. So go ahead and pause the video, try to work through example number 2, and then come back. Okay, so back we are. Hopefully you did number 2. Hopefully you really paused it. Did you really pause it and try example 2? I hope you did. Let me just kind of quickly show you that and how that's going to end up working out. First of all, we're going to write the equilibrium expression. So KEQ, going to put products on top. We're going to put coefficients. Coefficients become powers. Now this question doesn't specifically ask you to write the equilibrium expression, but you're not going to get anywhere in the problem unless you actually did it first. So hopefully you thought to do that. Next, we're going to go ahead and calculate KEQ. This is another situation where it's a 1-liter container. It's a 1-liter flask. So given the molarity equation, our number of moles and our concentration are going to be the same. So I can go ahead and just plug in the values from the problem. So the problem tells me I have 0.1 mole of NH3. Can't forget to square that. And then we have in this problem 0.25 moles N2, and we have 0.15 moles NH3. So to find the value of KEQ, we just have to solve that. Again, I'm not sure you can see exactly what's going on in this calculator, but we're going to go 0.1, we're going to square it, we're going to do divided by, we're going to use a bracket. We have to put this bottom part in brackets, 0.25 or parentheses. 0.25 times 0.15 cubed, so we get 11.85. Now, again, probably two significant figures here. Let's round it to 12 and no unit. So that's the answer that you should have came up with there, and hopefully you did. Okay, so we're going to go ahead and go on to example number 3. Now, example number 3 is a little bit different, but still, in all these problems, we're going to want to write the equilibrium expression first, whether it asks us to or whether it doesn't. So products go on top, reactants go on bottom. So it should look like that, because the equation is this. Okay, so products on top, reactants on bottom, and that's how we look. This time it's actually giving us a value of KEQ. It's telling us it's 0.2. So I actually know that to start, unlike in the other problems. And then it says, at equilibrium, a 2-liter flask contains 0.0045 moles of N2O4. So this is a situation where we are, in fact, going to have to use this molarity equation. I have to use concentrations in my equilibrium expression. So the size of the container is 2. That's my volume. That's going to go down in the bottom. And 0.0045 moles is going to go here on top. So if we go ahead and just divide that out to solve for molarity, we're going to do 0.0045 divided by 2, and we get 0.00225. So that's my concentration. And that is the concentration of N2O4. So I can put that down here in the bottom. Now the question is asking us, what is the concentration of NO2 at equilibrium? So let's go ahead and call that concentration X, and not forget that that has to be squared. So now we need to solve this. We need to multiply both sides by 0.00225. So we get x squared equals 0.2 times 0.00225, and we get 4.5 times 10 to the minus 4th. 0.00045 if you prefer. So x is going to be the square root of 0.00045. So we take that, so x equals 0.021. Probably two significant figures here, and that's a concentration, that's a molarity. So that is going to be the concentration of NO2 at equilibrium. And if any part of this problem didn't make sense to you, I'd suggest you go back through and see if you can figure out what's going on before we go on to example number 4. So example number 4 is a shorter problem, simple seeming. It says CaCO3, which is a solid. So all 4 is asking us to do is to write the equilibrium expression. So no math or anything like that. Now what the mistake that a lot of you will make will be to put these two guys on top and put this guy on the bottom. But what you would have forgotten, if that's what you did, is the very first bullet here. Consider the concentration of any solids and pure liquids to be 1, and do not include them in the equilibrium expression. Gases and aqueous solutions should be included. So, what I'm saying here is, instead of doing this, which is tempting, that's a solid, that's a solid. Solids do not go in these things in any way whatsoever. They're just gone, not in there, not a part of it. So actually, all it is this. That is my equilibrium expression for that particular reaction. Okay? Well, that about wraps it up for our Introduction to Equilibrium. Thanks for listening, and we will see you soon. Bye-bye.